to t. E to t. Very good. Close the parentheses, and we have from 0 to 4. Is this okay so far? So now I have to plug in 4, and then I subtract when I plug in 0. So let's simplify this a little bit. I hope you agree that this is 3 over 2, but I have to flip it. So it's 3 times 2 over 3 times t to 3 halves minus 2e to t, and these two will go away, from 0 to 4. I plug in 4. So t raised to 3 halves is like the square root of t raised to the 3rd power. So I plug in 4. The square root of 4 will be 2 cubed times 2 in front. Very good. Minus 2e to the 4th. Minus, in parentheses, so I don't forget to distribute the negative sign from the theorem. When I plug in 0 in the first term, it's 0. When I plug 0 in the second term, e to 0 is times 2. Perfect. So then we have 16 minus 2e to the 4th power and plus 2, which is 18 minus 2e to the 4th. Any questions?
Would you rearrange that at all?
No, that's it. They're just numbers.
Yep.
Okay. Here's 37 on page 404. The integral from 0 to pi over 4 from 1 plus cosine squared over cosine squared theta d theta. Every time the denominator is just one term, always consider, it may be necessary or it may be useful or not, but always having in the back of your mind the possibility of writing this. This over this is this, cosine squared over cosine squared is 1. And obviously this is nothing else but secant squared theta plus 1. I prefer this versus that fraction. So that was one of your questions, Tom. Depending on the fraction. In this case, I was able to very easily simplify it. But if I can't, then I have to think of that partial fraction decomposition. Okay, so this is 0 to pi over 4. I simplify the function into secant squared theta plus 1 d theta. I know which function prime is secant squared, and that function is? I know which function prime is 1. Very good. Close the parentheses, and from 0 to pi over 4. We plug in pi over 4 first. When I plug in pi over 4 in tangent, tangent of pi over 4 is the nice one, when top and bottom are the same, 1, plus pi over 4. But when I plug in 0, tangent 0 is it's sine 0 over cosine 0, and cosine 0 is 1, and the top is 0. So 0 minus 0 will be 0. Any questions? So what do we conclude about every time I determine I calculate or evaluate a definite integral? What will always the answer be? Okay, let me help. A function or a number? a number, right? Look back at all the definite integrals that we evaluated. The answer was a number. Question, can I check? I have no way of checking. I can only hope that the answer is correct. There's no way I can check a definite integral. There is none. Okay, there is a second type of integral, which is called indefinite. The indefinite integral does not have limits of integration. So the integral from f of x dx, what do you think the answer would be? And we have to use the proper notation. Very good. Plus a constant c. This is the indefinite integral. But what would be the answer then? If for the definite integral the answer was always a number and I couldn't even check, what would be the answer for an indefinite integral? Always a function. It's always a function. This one we are lucky. We can check. And now this is the fundamental theorem of calculus part 1. Fundamental theorem of calculus part 1. Okay, this is just a name. But what does it show? The previous one, it showed what? How to calculate a definite integral. This one shows that integration and differentiation. Yes, Tom, go ahead. Are inverse operations. Thank you. This is what it shows. So, fundamental theorem of calculus part 1 shows that differentiation and integration, or integration and differentiation, are inverse operations. That's why I'm going to copy it one more time. The integral from f of x dx equals f of x plus c. If I differentiate the left-hand side and differentiate the right-hand side, I have to get the same thing. So let's start with the easy part, that it's clear. What do I get here? Indeed, lowercase f of x. Perfect, awesome. So now, here we are taught that every time I differentiate an integral, what happens? These two are canceling one another. And of course, when I cancel this, the dx goes away as well. And what do I have on the left? Indeed. That's what it says. So we can always check definite integrals. Let's look at, I meant indefinite, of course. Sorry. So let's look at a few examples with indefinite integrals. And also check. Let's say 15 on page 404. The integral from theta minus cosecant theta, cosecant theta cotangent theta d theta. Which function prime is theta? Squared over. Which function prime is negative cosecant cotangent?
Cosecant.
Yes, plus a constant c. Very good. Now I want to check my work because I can. So I'm going to differentiate this side and differentiate this side. When I differentiate the left, what do I get? This is what we just learned from the fundamental theorem of calculus part 1. If I differentiate this side, what do I get? Theta
Theta minus
cosecant theta times cotangent theta. Now let's see what we get on the other side. When I differentiate theta squared over 2, what do I get?
theta,
And when I differentiate cosecant theta, negative cosecant theta cotangent theta. And when I differentiate c, what do I get?
0.
So as expected, they are the same. And we can do this for any indefinite integral. We can always check. Any questions? Any questions? Any questions? I want to jump to the last section of this chapter, and then we'll come back to tie up some minor loose ends. However, before that, let's look at odd and even functions. Not just odd and even, but also when the interval is symmetric. For symmetric interval, and of course, definite integrals and definite integrals. So whenever I'm asked to determine or evaluate a definite integral on a symmetric interval, and the function is odd or even. If the interval is not symmetric and the function is not odd or even, I cannot use this concept or this result. So let's take a look at an odd function. Can anyone give us an odd function on the interval negative a to a? Tom?
Well, I was thinking more of getting an odd number. X cubed.
Very good, thank you very much. Good. So here it is. If we're asked to determine the integral from x cubed dx from negative a to a, what will be the answer? And absolutely what? Of course. Because the quantity that's under the x-axis is negative and the quantity on the above the x-axis is positive, they are absolutely equal in absolute value. And because the interval is symmetric and the function is odd. Now you understand that if I change this between negative 5 and 10, the answer will not be 0, even if the function is odd. But because the interval is symmetric around the origin and the function is odd, the answer is 0. Agreed? Very good. So let's take a look at the other one now. Can anyone give us an even function on the interval negative a to a?
X squared.
X squared indeed. So here it is. So here is the area. So the interval is symmetric, and the interval between negative a to a from x squared dx. What would you say? And this is a tremendous help, because I really, really don't want to determine an area between negative a and a if I have an option. So this is definitely twice the integral from, I prefer this exactly. I always prefer to have the lower limit 0 from x squared dx. So for definite integrals, if the interval is symmetric and the function is odd, the answer is 0. For definite integrals, symmetric interval and the function is even, I can calculate twice the integral from 0 to a from x squared dx in this case. Okay, so 5.5, substitution rule. Like any substitution, it's supposed to make our life easier. If it doesn't, then it's probably not the right substitution. Or maybe the integral is easier than we think it is. Or we cannot find an antiderivative, which is very possible. I can give an example that only a calculator can find the antiderivative for this. I meant the software. computer software. We can't find this by hand. No one can. Okay? We cannot algebraically or by hand determine a function whose derivative is this. No one can by hand. So, no substitution will help here because I will never be able to determine that. Okay, so let's see how the substitution rule works. And I'm going to pick first from indefinite integrals and then from definite integrals. Let's say 32 on page 414. So here's the integral. The integral from sine applied to natural log x divided by x dx. Okay. This is not the most scientific way of looking at the function and coming up with a substitution, but it's the basic way that I think will help you in the long run. So what do I see when I look at this function? So this is f of x dx, base times height, and the sum, right? So what do I see here is that there is a function inside function sine. If there is a way of removing this, then the function will become much easier to handle. So I'm going to say, your book uses u. I prefer y, doesn't matter. You want u or you want y? Doesn't matter to me. U? Okay, so let u be natural log x. So this is my substitution. Is it good? I don't know yet. I have to make sure that it's differential. See, this function has the differential dx. This function will have the differential du. So I have to find the differential. Remember, there is a big difference between u prime and du. So we emphasized this a long time ago. U prime is the derivative of function u, but du is what I need for the integral, which is the differential of u. So looking at this, how do I write du? That's it. Awesome. So the differential of u is the derivative of the function times dx. So I would know that this is the correct substitution only if du is in the problem. If du is not in the problem, then I will have some difficulties. But it's no problem. Look, 1 over x times dx. This piece is this piece, or dx over x. So this is our du. But now I cannot have x and u in the same integral. What is this? Perfect. So remember, when I leave x behind, I have to make sure that x is not in the new integral. I can't have x and u. So can anyone dictate now the new integral that we have to determine? Perfect. Which function prime is sine u? Negative cosine u plus a constant c. The original function was in x. We used a tool that enabled us to find the integral. But now I have to go back to x. Because the function, the result of the indefinite integral, is a function and it has to have the same variable. That's not a problem because I know what I denoted by u. What did I denote by u? Good. So it's negative cosine, in parentheses, natural log x plus a constant c. Every time I determine an indefinite integral and I use a substitution, I have to present the final answer in the given variable. Okay. Let's take a look. What about 44? the integral from x divided by 1 plus x to the fourth dx. And I'll tell you what bothers me here, and you'll tell me if I'm on the right track. And what bothers me is that I have a sum of two terms in the denominator. That I don't like, because I can simplify. So I would like to say, let u be 1 plus x to the fourth. This would be a good substitution only if what?
Didn't have a negative sign.
If du is in the problem. Because I can make up functions and put them in there. If du is not in the problem, this is not the correct substitution. So du equals 4x to the third dx. 4 is not a problem. I can multiply the top and the bottom by 4. But I have a huge problem with the rest. What is the problem? It's this x cubed. Even if I break it up into x squared times x, and so let's say I have an x, but how do I get the x squared? So this is not the substitution I need. It doesn't work. So I'm going to copy the problem again. It's okay to think, it's okay to write one of the options till you figure out what the best option is, or maybe the only option. So 1 plus x to the fourth is not the right way. What could be the right way then? So that I have du in the problem. A number I can make up, no problem. But functions I cannot always make up, most probably not. So what would you think? So that the derivative has something to do with x. What function will have the derivative something with x?
X squared.
Perfect. How much is du?
2x.
Very good. No problem. I can make up numbers, multiplying the top by 2 and multiplying the bottom by 2. That's not a problem. But what is this then? Perfect. And now what is this? That's it. Do you agree with this? Okay, now let's see how we proceed. I copy the 1/2 in front. And what is left? So 1/2, the integral from, now I have to put everything together. Du. You're right. It could be 1 over times du on the side. It's the same thing. Over. Okay, now I have to dig deep. There is a function whose derivative is 1 over 1 plus u squared. And that function is arctangent. Very good. Plus a constancy. It's u. I'm sorry. Okay, good. 95%. I'm missing one more step, which is I have to substitute. So this is 1/2 arctangent. What did we denote by u?
X squared.
Very good. So x squared plus a constancy. Any questions? Any questions? Ready for another? Okay, what about 48? It's the integral from x cubed, the square root of x squared plus 1 dx. Here, what I don't like is, or maybe you want to tell me what we don't like here. I don't like this, right? Because the square root of a plus b is not the square root of a plus the square root of b. So as long as I have a sum or a difference under the square root, I really don't like it because there is nothing I can do to simplify it. So that will be the starting point for me. So I will say let u be what? Yes. It's okay if you are starting on the wrong foot. It's okay. Like I showed you a previous example. I intentionally started on the wrong foot to show you it's okay. Just try it, and then you say, oops, it doesn't work. I'm going to go back and find another substitution. I don't know if it works. Let's try it. So du equals 2x dx. Agreed? Now let's see what we have. I have to make up this 2. Not a problem. 2 times 1/2 is 1. I also have to look at this carefully and say, oh, x cubed can be split into x and x squared. So then 2x and dx, 2x and dx will form. This will be, and now I still have a piece to handle. It turns out that I can. How much is x squared from here? So now I have all pieces changed completely from x into a new integral with u, which will be much easier to handle. So I have 1/2 in front. So now can anyone dictate the new integral in u?
Minus 1 times the square root of u.
Much easier. Although you may say, oh, it doesn't look like it. You'll see why. So this is 1/2. The integral, I will distribute the square root of u. So I have u to 3/2 minus u to 1/2. Because the square root of u is u to 1/2, and I multiply it by u, copy the base, add the exponents. 1 plus 1/2 is 3/2. And this I can determine. This, no. I really don't know what to do with that. So there is 1/2 in front, and u to 3 over 2 plus 1 over 3 over 2 plus 1 minus u 1/2 plus 1 over 1/2 plus 1 plus a constant c. Yes, I have to fully simplify it and go back and replace u by x squared plus 1. Questions, please, before we do that. So 1/2. 3/2 plus 1 is 5/2. So times 2 over 5 times u to 5/2. Minus, this is 3/2. 2 over 3 times u to 3/2. Plus a constant c. And I have to distribute 1/2. 1/5 u to 5/2 minus 1/3 u to 3/2 plus a constant c. And I have no choice. I have to go back and replace u by x squared plus 1. So 1/5 x squared plus 1 to 5/2 minus 1/3 x squared plus 1 to 3/2 plus a constant c. Ugly. Quite ugly. Now let's talk about the substitution rule for definite integrals. Any questions? Any questions? Let's look at 59 on page 414. So the integral from 1 to 2, from e to 1 over x, everything divided by x squared dx. Because it's a definite integral, I have to make sure that the function is
Continuous.
on the interval 1, 2. Well, this function is only undefined at 0. The interval is 1, 2, so the function will be continuous. Okay. So I'm looking at this function, I say, I really don't like having a power of e instead of e to the x, having 1 over x in there. So this is what my starting point would be. To say, let u be just 1 over x. E is friendly. E to u is friendly, right? E to 1 over x is not friendly. So as long as du is in the problem, then I'm in business. If du is not in the problem, then I have difficulties. A number I can adjust, a sign I can adjust, but I cannot adjust pieces of functions or functions. So that's why I said, please always remember the derivative of 1 over x.
1 over x squared.
Dx. Very good. Okay, so I do have 1 over x squared. I have the x. I don't have the minus. No problem. I'm going to multiply by -1 twice. That will make no difference. No change whatsoever. What is this now? What is this? So can anyone, without copying the limits of integration, please, minus the integral from, give us the integral. Do not copy the limits of integration. Yes. Do you all agree with e to u du? Is this much easier to handle than this? Agreed. Okay, now, for the definite integrals, when we change the variable, or we use a substitution, from x, we have certain limits of integration. When we move to the new integral with variable u in this case, the limits of integration cannot not be copied. They are the limits of integration for x. The limits of integration for u are totally different. Let's determine them. So, when x is 1 for the lower limit, how much is u? When x is 2 for the upper limit, how much is u? That's it. And we do not go back to the previous function or the previous variable anymore for definite integrals. Okay, so then this is negative. What function prime is e to u? E to u from 1 to 1/2. Now I'm applying the fundamental theorem of calculus part 2, in which I keep the negative outside, and I plug in 1/2, which is e to 1/2, minus when I plug in 1, and I get e. But this is negative the square root of e minus e, which is e minus the square root of e. The answer for definite integrals is always a number. It doesn't matter if you are determining that number using a function in x or a function in u. But why would you go back? Can you? Yes. You will not copy the limits, but then you're complicated things. So once you moved away from x to u, and you have the appropriate, you cannot write, you cannot copy the same limits of integration because they are different. They are for function u. This was for function in x. Now this is for function in u. So once you copy them and you get the answer, there is no point in going back. You have to go back if you're determining an indefinite integral, you have no choice because you have to replace u, because this is not a number. This is a function in x, and it has to be in x. But here, this number doesn't care if we determine it from function in x or function in u. So do not go back. There is no point. Okay. Ready for other examples? Okay, so let's look at 63. We have the integral from 0 to 13 from dx over the cube root of 1 plus 2x, everything squared under the cube root. It looks ugly, right? So what don't you like here? Of course. So let u be 1 plus 2x. As long as du is in the problem, we are on the right track. If we're not, we'll go back and come up with something else. So du equals the differential of u equals 2 dx. Not a problem. Multiplying the top and the bottom by 2 will never change a function. So now I know that this is represented by or can be replaced by, very good. And I know that this can be replaced by, very good, or u to 2/3. So the new integral, do not copy the limits of integration, please. Give me the new integral. And you can also move u up as u to negative 2/3 times du. But now I know I need the new limits of integration specifically for u, not copied from x.
So we have 1 as the lower.
Indeed, when x is 0, the lower limit for u is 1, perfect. And when x is 13, the upper limit is?
27.
Awesome. So this is 1/2 u to negative 2/3 plus 1 over negative 2/3 plus 1 from 1 through 27. Negative 2/3 plus 1 is 1/3, and I have to flip that. So in front we have 3/2. And this is u to 1/3, or the cube root, from 1 through 27. Do not mess with 3/2, there is no point. Let it wait. Let's plug in 27, and we have the cube root of 27, which is minus, that's, don't forget the minus from the fundamental theorem of calculus. When we plug in 1, what do we get? The cube root of 1.
1.
Good. 3 minus 1.
So then you get 3 is the answer.
Exactly. Simplify, and the answer is 3. Any questions? Any questions? Okay, let's work on one more. Here, before I think I have another minute to show you a property. '69. It's in red. I don't know why, so let's take a look. The integral from e to the 4th power from dx over x, the square root of natural log x. So of course I'm after function composition, right? 1 over x is not a function composition. It's just plain 1 over x. But natural log inside the square root, that is a function composition. That's what I don't like. So what will you say? Let u be? Yes. Let's see if it works. Du must be in the problem with little or no effort. 1 over x dx, which it's very clear that I do have. So this is du, and this must be u to 1/2. and I have to bring it to the top. So then we have the integral from u to negative 1/2 du. Now I have to be careful because I can no longer copy or use the same limits of integration. When the denominator, the lower limit is e, natural log e is perfect. When I have natural log of e to the 4th power, indeed, awesome, very good. So negative 1/2 plus 1 is 1/2. So this will be the square root of u from 1 to 4. See how elegant the whole thing is. We plug in 4, we get minus when we plug in 1. And the answer is 1. Okay, one last thing for today. I know we have like 7 minutes left. Okay, so here's a function. Continuous function on the interval a comma b. And let's suppose I want to determine this area. Can anyone dictate the area under the graph of f of x? What does it equal to?
Integral a to b
From a to b, from?
f of x.
Yes, base times height dx. Good, perfect. Now I'm going to repeat, but this time I'm going to use a to b, but I'm going to change the variable. I'm going to say that this is f of t now. Same function. I'm using t. And I'm going to say that there is an x between a and b. And let's say x starts anywhere is from a to b. So let's say at some point in time, this is my x. And the integral from a to x from f of t, dt, is this area. Would you agree? The integral from a to x, if x is here, from f of t dt is this piece. Agreed? Okay, now let's say I move x here. So this will be the area represented by the same function. But it will be a different answer, correct? Because let's say this area was 2, oh, this area is 5. So for x being this number, I get 2, and for x being this number, I get 5. Agreed? A different number. Okay. Now let's say I move x here now. And then I get this area. So for a different x, for the third x, I will get 15. So can anyone tell us what this is and what did we just create? And here's the answer. When x is 1, I get 5. When x is 2, I get 10. When x is 3, I get 15. When x is 5, I get 55. When x is... What am I creating here? Yes, but also called a... Yes, it is an integral. So if I have x and I say x is 1 and you say y is 3. I give you another x and I say x is 10 and you are giving me 15. And then I say another x, 25, and you say 110. What am I creating then? Thank you. So this is not a number, but a function, because it will be the different number for each x. So this is a function given in a form of an integral. G of x, a function given in a form of an integral. So g of x equals the integral from a to x from f of t dt. And now, bless you, I would like to find g prime of x. if I want to differentiate this side to find g prime, what do I have to do to the other side? Very good. But what did we say about differentiation and integration? Right. So when I differentiate an integral, I will get the function. So what is the answer? And here's your hint.
F of x.
Very good. It is f of x. One example like this, and I'll stop. And next Tuesday, we have just a few little things to tie up. Something about the total distance and some properties. Okay, just one example. Let's say, notice one thing. This must be a number, comma, or in parentheses, not a function. That's a must, the lower limit. So here it is. In problem 8 on page 394, we are given a function in a form of the integral from 3 to x from e raised to t squared minus t, of course, dt. No one can ask us to evaluate something like this. We can only be asked to find the derivative of this function. So can anyone give us the derivative of this function?
We need substitution first.
Exactly. E raised to
U. Or,
x squared minus x. I should write times the inner function prime. The inner function prime. But what is the inner function prime? What is the inner function prime?
1.
Exactly. That's why I'm not going to write it. Now I'm going to change this into x cubed. What if I have this expression or this function? Can anyone give us the g prime now? And be careful that when you plug in, you are no longer plugging in a plain x. You are plugging in a function. So what will be the answer this time?
The x to the 6.
Very good. Minus,
X to the
very good. Multiplied by the inner function prime.
3x.
That's it. Yes, I will put 3x squared in front.